In our previous lesson, we looked at the many different forms of work that we're going to be considering in thermodynamics, broadening our definition of work, and finally looking at energy balance. The first law of thermodynamics says that energy cannot be created or destroyed, it can only change forms. And so we defined the overall change in energy, delta E, as the change in internal energy, delta U, and that can take many forms, plus the change in kinetic energy, plus the change in gravitational potential energy. And this is going to be the change in energy for a closed system. However, there's also ways that closed systems can interact with their surroundings that aren't work. And we're going to take a look at one of the most important of those now, which is heat. So, with heat, we're going to use the letter Q to denote heat transfer. And Q is the amount of heat energy transferred across the boundary by the system interacting with the surroundings by heat. And so if our heat is being transferred into the system, Q will be greater than 0. If our heat is being transferred out of the system, our convention is that Q is less than 0. So Q is not a property, it's something that's being transferred across the boundary, either into the system, in which case Q is positive, or out of the system into the surroundings, in which case Q is negative. And we can look at calculating Q a number of different ways. First, we consider Q, the amount of energy transferred, as the integral from state 1 to state 2 of del Q. We can also consider that Q is the integral across a time interval from T1 to T2 of Q dot, which is the rate of heat transfer dt. One other thing we'll also look at is something called little q dot. And little q dot is the heat flux. So it's the heat transferred per unit time per unit area, so further normalizing this heat transfer rate. And so then q dot is the integral over some area A of little q dot, the heat flux, dA. And these are all just generic integrals where we're looking at the heat transferred across two states or two times or across an area. And so these three different ways of looking at Q. Q, just the heat transferred, has units of joules. The heat transfer rate has units of joules per second. And the heat flux has units of joules per second per meter squared. And now we want to look at the three different ways we have for transferring heat. So that's we can look at, so these integrals look at how we can calculate the amount of heat transferred. Now let's look at the different heat transfer mode. So the first heat transfer mode we're going to look at is conduction. And for conduction, we have, this is one of the more common ways of transferring heat. It can take place in solids, liquids, and gas, and it's basically the transfer of energy from the more energetic particles to the less energetic particles. And so again, heat is really just the kinetic energy of individual atoms and molecules and particles. And so conduction is having a solid, liquid, or gas in physical contact with another solid, liquid, or gas, and the heat being transferred from the more energetic particles in the hotter matter to the less energetic particles in the lower temperature matter. So this is, heat being transferred from the outside through the walls of your house into your house on a hot summer's day. It's the heat being transferred when you turn on the burner of your stove, and it's transferred through the pot, then into the water to boil. So this is conduction. And when we have steady state conduction, which is the one we're going to consider, we use Fourier's law to look at the heat transfer across any plane normal to, or any plane. And so if we have some distance x, and we've got something hot here, transferring heat through, it'll set up a temperature gradient from T1 down to T2. So this is for a, hot outdoors. Sending heat through the wall into our cold room. And so for this situation, Fourier's law states that the heat rate being transferred across X equals kappa. In some books, it's the letter K is used. If you've seen this before in Material Science and Engineering book authored by Callister, he uses the Greek letter lambda. And all of those are denoting the thermal conductivity. It is a property of a matter, so you can look it up, of the solid, the liquid, or gas, and it's related to how well that material transfers heat. So it's kappa, but our book uses kappa, so I'm going to use kappa for this class. Kappa times times A, the area of this material, times the temperature gradient, dt dx. And so this is the equation that allows us to calculate the heat transfer rate and relate it to the change in temperature, the temperature gradient in this material. And so that's conduction. Our next form of heat transfer that we're going to consider is radiation. And radiation or thermal radiation is emitted by matter ultimately because of changes in the electronic structure of the atoms. And so it's being actually transported by electromagnetic waves or photons. Those things can also transfer light, but in this case we're looking at the electromagnetic radiation that's transferring heat. And unlike conduction or convection, thermal radiation doesn't require any intermediate in a medium. It doesn't have to have anything to transfer through. Thermal radiation can actually heat something up inside a vacuum. And so we're going to look at, when we look at calculating the rate of heat transfer for thermal radiation, we use the Stefan-Boltzmann law, which says that the rate of heat transfer by an emitting surface, that's what the E is for. So so a surface that's emitting these photons, is equal to epsilon, which is the emissivity of the material, times sigma, which in this case is the Stefan-Boltzmann constant, times the area of the surface A, times T of the surface that's emitting the waves, to the power of 4. And so again, the emissivity is a property of the surface. We can look that up. The Stefan-Boltzmann constant has units of 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the 4th. And I should say this temperature here, T sub B, is the absolute temperature. So that temperature needs to be in Kelvin, or if you're working in English units, in Rankine. And so that's radiation. Our third way of conducting conducting heat is by convection. And so convection happens when you have heat being transferred to or from a solid surface, usually, by a flowing fluid, and that fluid can be liquid or air. And it's a prominent role, or it's very important for a number of devices for heat transfer that we're going to cover in this class. And so the rate of heat energy transferred from the surface to the surrounding fluid by convection is given to us by Newton's law of cooling, which says this rate is equal to H, where H is the heat transfer coefficient times the area of the surface times the temperature at the surface minus the temperature of the fluid. And so H is a property of the material or surface, and we can look that up. And that's convection. So now we have 3 different equations for our different ways of transferring heat from the system to the surroundings or vice versa. And this is very important because now we have, with most of the systems that we're going to look at in this class, the ways that energy, and for most of the situations that we're going to look at, we have some system with some energy E, and we can have the system perhaps doing work, and we can have the system receiving some heat. And the change in energy of the system is going to be affected by how much work is going in or out of the system, or how much work the system is doing or work is being done on the system, and how much heat is going into or out of the system. And so our energy balance equation now for closed systems becomes a little bit more complicated but useful, where delta E is now equal to Q minus W. And so perhaps even a more useful form would be that now the change in kinetic energy plus the change in gravitational potential energy plus the change in internal energy, so that's overall the total change in energy of a system, is equal to Q, where Q is positive if the system is doing work, minus W. Q, where Q is positive if heat is going into the system, minus W, where work is positive if the system is doing work. And so this equation here is the one that we're going to use in many of the rest of the problems for this class, in addition to the problems or the equations that calculated the amount of heat being transferred by either conduction, radiation, or convection. And this larger expansion of the first law of thermodynamics basically is going to allow us to look at how energy is being transferred for different types of systems and machines. So we'll start looking at that shortly.